Okay, so next we have the 18th one. Here we are given the dihedral group Dn, and by H we are denoting the subgroup of Dn consisting of all the rotations in Dn. And let phi be an automorphism of Dn. We have to prove that the image of H under phi is H itself. In other words, any automorphism of Dn carries rotations to rotations. And in the solution we are going to, in the beginning itself we are going to use that result which gives us the basic properties of automorphisms of groups, and that is theorem 6.3 by theorem 6.3. The image of H under phi is an abelian subgroup of Dn. Okay, let me just explain how the individual parts are being concluded here. From this theorem, we first of all note that since H itself is a subgroup, its automorphic image is also a subgroup. That is one thing. And the same theorem, another part of that theorem also says that in particular, if our original group H is abelian, then the image is also abelian. So that's why this is an abelian subgroup of Dn. Okay, how do we know that H is abelian? In fact, we know a little more than the abelian nature of H. We know that H is not just abelian, but H is actually cyclic. The subgroup consisting of all the rotations is a cyclic group generated by the smallest non-trivial rotation. But anyway, we now have this, and now let's just see what the order of this subgroup is. Because we are, okay, let me just write and then we will see. Note that since phi is an automorphism, it's one-to-one. Actually, it's both one-to-one and onto, but let us now concentrate on one-to-oneness. Phi is one-to-one, and hence this function is bijective. What is this function? This is not the entire phi. We are restricting the original phi to the subgroup H from the entire group Dn. And we know that the restriction of any one-to-one function to a subset of the domain of that function is itself one-to-one. So that's how this function is one-to-one. Okay. And another thing is that since we are considering the image here, so it is automatically onto. So that's how it becomes bijective. Now the consequence of this is that the size of H, or the number of elements in H, will be the same as the number of elements in phi of H. As a result, the order of phi of H is equal to the order of H, and we know that that order is n. There are n rotations and n reflections in the dihedral group. Half of the elements are rotations and half of them are reflections. And we also know that the order of Dn itself is 2n because of that. Now here is another fact about subgroups of the dihedral group Dn, and that fact is this: since Dn has a unique Dn has a unique abelian subgroup of index 2 or order n, same thing. Dn has a unique abelian subgroup of index 2 and h and phi of h are both such subgroups. Hence, phi of h is equal to h. I think that I am leaving some one or two cases out from this solution. That is, the first few values of n do not have this property. Okay, I am not going into too much detail into that. You just see where this property starts in Dn for the very small values of n. I think n equal to 2, for n equal to 2, in D2 this I think is not true, but I haven't seen I haven't gone into that. Okay, so I leave this itself as the solution and leave to you to rectify this part for small values of n. After some stage, I think from n equal to 3 or n equal to 4 itself, this starts. So this part is in fact left to you, right? And you also have to justify how this is true. So that part is left to you. So in that sense, this in fact is an incomplete solution, but just a sort of an elaborate hint of the actual complete solution. But I am going to stop here itself. You have got the idea, now it's up to you to complete it. Let's see the next one. Let H be the set of those permutations beta in S5 that fix the symbol 1, it does not change 1, and K be those permutations again in S5 that fix 2. We have to prove that H is isomorphic to K. That means these are going to be subgroups of S5, but they are isomorphic to each other. And the same thing is also being asked if S5 is replaced with any Sn, where n is at least 3. Prove that H is isomorphic to K is the same true if yes. Is the same true if S5 is replaced by Sn, a general n where n is at least 3. Looking at H, you will see that it's okay. What are the things that we have in H? H consists of precisely those permutations in S5 that fix one and may or may not fix the other 4 symbols. So from that you will get an idea that H is in fact isomorphic to S4, the symmetric group of degree 4. So what we are, in fact that is the case. So what we are going to do is that we will first prove that H is a subgroup of S5, and then we will set up a function between H and S4, show that it's an isomorphism. So that way we will achieve the fact that H is isomorphic to S4, and then one can similarly show that K is also isomorphic to S4, and that way they two will be isomorphic to each other. So let's just do that. Showing that H is a subgroup is very easy. I am vaguely remembering that we have done something similar previously also, but anyway, let's do it once more. Since the identity permutation E, let me just write E, belongs to H. H is a non-empty subset of S5. Why does E belong to H? That's because E fixes 1, E actually fixes everything because it's the identity function. So E fixes 1, and that's why it belongs to H. So H has something in it, so H is non-empty. And now we can apply our subgroup test. Let beta 1 and beta 2 belong to H. Then beta 1 of 1 is 1 and beta 2 of 1 is also 1. And from this we have two things. This implies that beta 1 composition bit, if you want you can just simply write beta 1 beta 2 of 1 will be what? This, but beta 2 of 1 is 1, so that is beta 1 of 1, which is also 1. And the other thing that we get from this is that the beta 1 inverse image of 1 is also 1. For that you just apply beta 1 inverse to both sides of this first equation. So that will give you this. So we see that the image of 1 under beta 1 composition beta 2 is also 1, and the image of 1 under beta 1 inverse is also 1. Hence, both of these things belong to H, and so H is a subgroup of S5 and hence a group in its own right. And now we are going to set up that function that we were talking about. Now define, but before, okay, I think it will be useful if we name something else first. Let capital A be the set consisting of these 4 symbols, 2, 3, 4 and 5. From this list we have excluded 1, and now we are going to define a function t from h into S4 by this formula. T of beta equal to beta suffix a, and this beta suffix a has a meaning where beta suffix a is the restriction of beta onto a. See, originally our beta is a function, it's a bijection from this set to itself, but now we are restricting that beta to this subset. We are naming it so that we don't have to write it again and again. We can just simply write a. Now, is this a well-defined function? That is our first concern. For this function to be well-defined, what is it that we should have? You take an input. That input is beta, which is coming from h. And what is the output? The output is the restriction of beta to this, to a. Now the question is this. Oh well, okay. Now I think I cannot write this set here. I think it will just simply be a. But then the question will arise, how is it a function from a into itself? That has to be answered. So that is the first question. What is the guarantee that beta of a will map a into itself? And then there is another question. Is this really a bijection on the set A? That is the other question, because otherwise it won't belong to S4. Okay. So let us first show that this actually is a function from a into a. For any I belonging to A, so what will I be? I is any one of these 4 symbols. Beta of I is not equal to 1. Why? That is because since beta is coming from H, so beta of 1 is equal to 1, because that's what H is. H consists of those permutations that fix 1. And beta is one such permutation, so beta of 1 is equal to 1. But I coming from A is not equal to 1. So I is different from 1 and beta is 1 to 1. The original beta is 1 to 1. It's a bijection, so it's 1 to 1. So how can beta of I and beta of 1 be the same when I and 1 are not the same? That is why they are not the same. Beta of 1 is not equal to 1. However, beta of 1 must in fact be in that set consisting of the first 5 natural numbers. So that's why, I mean beta of I. So that's why beta of I is forced to be in A itself. You can write here, since beta is 1 to 1 and I is not equal to 1, because of that it's happening. Thus beta of I belongs to A. Okay, so this at least shows that we have a function from A into A. Next, since the original beta is 1 to 1, so is the restriction. You do understand that I am writing beta here, but I can also write beta A here, because by the definition of restriction, the image of any point in that subset on which you are considering the restriction, under that restriction is nothing but the actual image of that point under the original function. That is the definition of restriction. The formula does not change, only the domain changes. So is beta of A. Okay. Next, let J be any element in A. We now want to show that there is an element again in A whose beta image is equal to J, and that would prove that this beta A is onto as well. Since beta is onto, there exists some K belonging to this set such that that is the domain of the original beta, such that beta of K is equal to J. But again, you note one thing, that since this J is coming from A, J is not equal to 1. But J is not equal to 1 and 1 is equal to beta 1. So K cannot be equal to 1, obviously, because a function cannot have two outputs for a given input, i.e. this K, although it is coming from this set, actually it's in A. Thus this is onto, that is a bijection from A to A. This is a bijection from A to A. This shows that beta A actually belongs to S4. But you may not agree with me. You would say that there is a problem. That's because what is our beta A? Let's just forget about A for a moment and write what A is. We have just now proved that beta A is a bijection from this set to this set. But what is S4? S4 consists of all bijections from this set to this set. Strictly speaking, this beta A is not such a function. However, actually that does not matter. That's because, you see, these are some symbols, right, on which we have some permutations acting. We are really interested in the arrangements or the positions of the things that you have after you apply such a permutation, the relative position of those things with respect to one another. That's what matters, not the actual name of the objects. That does not matter. And also in the group S4, we are actually not interested in the symbols themselves, but rather the functions. Strictly speaking, if you really want to be strict about everything, then this beta A in fact is not a function from this set to this set. It's actually a function from this set to this set. But let me just take one example. Say this is our beta A. It maps 2 to 2, 3 to 3, 4 to 5 and 5 to 4. In place of this beta A, here you can imagine a similar function. That fixes 1, fixes 2, maps 3 to 4 and 4 to 3. Although the functions strictly speaking are different because they are acting on different objects, they have different sets as domain and different sets as range, but still their nature is exactly the same. And if you make this function, this permutation, interact with another permutation, interact in the sense forming composition, and you consider the other permutation that you will have on this side corresponding to that one, then this interaction and that interaction will have similar results, which is why we have a single name for this group S4, which only takes into account this number 4 and not the original names given to these objects. Only how many objects there are, that's what matters. You can, if you want to be really annoyingly strict about everything, you can think of two S4s. In one, you have functions from this set to this set that are bijections. In another one, you have functions from this set to this set that are bijections. But you can clearly see that there are relations. I mean, you can set up a one-to-one correspondence between that S4 and this S4, like this, and they will behave exactly similarly. Okay, so in that sense, we are writing beta A belonging to S4. In fact, that S4 and this S4 will be isomorphic to each other. That is the basic idea. The group structure stays the same. What name we use to call them, that does not matter. Right. So now our function T is well defined. Capital T that we have set up between H and S4, that is well defined. So T is well defined. The next job is to show that T is a homomorphism. Let beta 1 and beta 2 belong to H. Okay, then what is T of beta 1 composition beta 2? We know that this is nothing but the restriction of beta 1 composition beta 2 to the set A, and at the same time, what is T of beta 1 composition T of beta 2? That is the composition of the restriction of beta 1 to A, because we already have a suffix, so I am using brackets, and the restriction of beta 2 to A. Are these two compositions, are these two functions the same thing? Let's see. See, one thing is obvious, that is that both these functions, this one as well as this one, both of them map A onto A. How? This already maps A onto A, but how is that true? You see, just like beta 1 and beta 2 are permutations coming from S5, originally coming from S5, beta 1 composition beta 2 is also a permutation in S5. So just now all these things that we have shown prove that this restriction is a function from A to A, and not just that, it's a bijection from A to A. Similarly, beta 1 coming from S5 gives us the fact that this restriction alone is a map from A to A, and so is this. So their composition naturally is also a function from A to A. So now we just need to see that they give us the same output for a given input from A. So let's just consider any input. For anything we can take. Let us just take I. What is this? By definition, this thing is nothing but this, which by the definition of composition is this. But because I is coming from A, we have this. But since beta to A maps something from A again to something in A, so this beta to A image of I is again in A, and that's why this entire thing is equal to which again by the definition of composition is this. Thus, not only are these two functions mapping A onto A, but actually they are the same thing. So that's why So what is it that this final equation is telling us? It tells us that this T is a homomorphism, a group homomorphism. hence T is a homomorphism. The next thing we will show is that T is one-to-one. Now I am thinking about how to show one-to-oneness. Do we go for that kernel thing that way, that path do we take, or we just simply show that it's one-to-one, just like we show that a function is one-to-one. If I take the kernel, yeah, let's just use the kernel. Let beta belong to the kernel of T, then then what? Then T of beta, which is the restriction of beta to A, is the identity function on A, i.e. beta A of I is equal to I for all I belonging to A. Okay. But also beta of 1 is equal to 1 because beta is coming from H, right? Beta is, our inputs are all coming from H, so actually they are all permutations in S5, but they fix 1. So beta A fixes I and beta fixes 1, and this I is any I from A. So from this part and from this part, combining these two things, we have this: beta of I is equal to I for all I belonging to this, where this part is your capital A and this is 1. Which means what? Which means that beta is the identity function in S5, that is the identity permutation. So that means the kernel of T consists of only the identity element in S5. In S5 and in H also, same thing. Let's just note that it's in H because H is our domain of T. So T is 1-to-1. Next we look for onto-ness. Let gamma belong to S4, and keep in mind that now our S4 consists of those permutations that act not on 1, 2, 3, 4 but 2, 3, 4, 5. We have already seen that it's the same thing. Then the function gamma prime belonging to S, we cannot just simply write that it belongs to S5. Then the function gamma prime, let me just write like this: prime from 1, 2, 3, 4, 5 to that same set, such that gamma prime of 1 is equal to 1 and gamma prime if we restrict gamma prime to A, that means to this part, it is gamma. If this is our definition of gamma prime, does this definition make sense? It makes sense, because what we are doing here is that we are defining gamma prime to be just gamma when our input is coming from here, that is when our input is coming from A, and gamma itself is well defined, so there is no problem in this part. And what else do we need to do? We need to define it at 1. What does it do to 1? Our definition is that it does not change 1. So this achieves 2 things. Well, actually 3 things. Let me just write. Then this function is a bijection, which you can easily argue how. You just use the fact that gamma is itself is a bijection from 2, 3, 4, 5 to 2, 3, 4, 5, and we have just additionally included one more point. So that makes gamma prime a bijection. I am not going to elaborate any more on this. And so gamma prime belongs to S5. In fact, so that is the first thing. The second thing is that because of this equation, gamma prime belongs to H actually, capital H. Well, this solution is in fact available at the end of the text, where solutions are available, but only as a hint, as a simple remark. I did not realize that it would be this big, but anyway, it is what it is. In fact, gamma prime belongs to H, and what is T of gamma prime? T of gamma prime by definition is this restriction of gamma prime to A. And that by the very definition of gamma prime is nothing but gamma. So this shows that for any element gamma in S4, we have an inverse image gamma prime in H under T of that gamma. Thus T is onto. Hence H is isomorphic to S4, right? Because T is well defined, it's homomorphism, it's one-to-one, it's onto, it is everything. So H is isomorphic to S4, and T is an isomorphism, establishing that fact. Similarly, K is also isomorphic to S4. Thus H is isomorphic to K. Having seen all these things, you obviously understand how you have to go for the similar thing for K. There, in place of this capital A, you will have to consider another set which consists of 1, 3, 4 and 5, because K consists of those permutations in S5 that fix 2. Here the permutations are fixing 1, but there we have the fixing of 2. So that's how these two are isomorphic, and clearly we can replace S5 with any Sn where n is at least 3 and have the same conclusion, same result. So that's how the solution ends. Shall we see a little more? Let's just see one more, because this is just one line. It's a one-line solution. Show that Z, the group of integers under addition, has infinitely many subgroups isomorphic to the group itself. And well, it's one line solution means I will give you the hint and you will have to do the rest. Consider PZ. It's the subset of Z consisting of all multiples of P, all integer multiples of P, where P is a prime. P is a prime number. You can take positive primes, of course, the ordinary prime numbers. No need to consider negative, say minus 2, minus 3, no need to consider those things, because if you do, you will get the same thing. So what I am saying is that PZ is the same as minus PZ. It turns out that these are subgroups of Z under addition, of course. You show that first, and then you show that actually this is isomorphic to Z. I am not going to say what the function you have to consider that will give you the isomorphism. It's extremely straightforward. Just by looking at the elements of this set, you should be able to guess that function. Okay, so please do that, and if you don't get the solution, please let me know in the comments below. We will do it fully in the next Gallian group video. So I am going to end the video here itself. Because of that solution, it has been somewhat long. But anyway, that's just it for tonight, and tomorrow we have another upload, our usual analysis video. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.